For millennia, humanity has gazed upon the stars, wondering if we are truly alone. Our galaxy, the Milky Way, is home to hundreds of billions of stars, and many of them don't travel alone. They're part of what astronomers call a binary star system, two stars locked in a gravitational embrace, orbiting a common center of mass. Imagine a sky with two suns, casting double shadows and painting twilight in hues we can only dream of. But can planets, especially life-bearing planets, truly exist in such a complex, double-starred environment? For a long time, the answer was uncertain. Now, we're finding evidence that not only can they exist, but they might also hold incredible secrets. Let's clarify what a binary star system truly is. It's not just two stars near each other by chance, but rather two stars gravitationally bound, orbiting a shared barycenter, their common center of mass. Think of it like a cosmic waltz, where each partner dictates the other's movement. These systems are incredibly common. In fact, more than half of all star systems in our galaxy are thought to be binary or even multiple star systems. Yet, finding planets within them, especially planets with stable orbits capable of supporting life, presents a monumental challenge due to the complex gravitational forces at play from two powerful suns. Forming planets in a binary system is like trying to build a sandcastle on a stormy beach. The turbulent gravitational environment makes it difficult for dust and gas to coalesce into stable planetesimals, the building blocks of planets. Any nascent world must either cling closely to one star in a S-type orbit, or orbit both stars in a wider P-type or circumbinary orbit. Both scenarios are fraught with peril, as gravitational tugs from the secondary star can disrupt orbits, eject worlds into interstellar space, or crash them into their suns. For decades, it seemed unlikely that many planets could survive such a chaotic cosmic upbringing. To find planets beyond our solar system, or exoplanets, astronomers employ several clever methods. The transit method observes slight dips in a star's brightness as a planet passes in front of it. The radial velocity method detects tiny wobbles in a star's motion caused by a planet's gravitational tug. And direct imaging attempts to photograph the planet itself, though this is incredibly challenging. Each method has its strengths and limitations, and often, multiple techniques are used to confirm a discovery. In binary systems, these methods become even more complicated, as the light from two stars can obscure a transit, and the gravitational effects are far more complex to model. Our story begins not with a bang, but with a whisper, a faint, almost imperceptible flicker in the light curve of a distant binary star system, cataloged simply as K341b. For years, this system, located approximately 850 light-years away, had been under routine observation by automated sky surveys. In the early 2030s, a dip in brightness, lasting for several hours, was recorded. It was so subtle, so brief, and so easily attributable to stellar activity or sensor noise, that it was initially flagged as a false positive and largely dismissed. It was just another glitch in the colossal stream of data pouring in from our orbiting observatories. Decades later, as machine learning and artificial intelligence revolutionized astronomical data analysis, a team at the Institute for Exoplanetary Studies began reprocessing vast archives of old survey data. Their new algorithms were designed not just to find obvious transits, but to identify complex, repeating patterns hidden within what was previously considered noise. It was during this painstaking re-examination of K341b's records that the anomaly resurfaced. The glitch wasn't random, it was periodic, subtle, and incredibly consistent over many observation cycles, hinting at something far more profound than stellar flares. The algorithms were detecting a rhythm no human eye could discern. With the algorithms pointing to a repeating event, astronomers directed new, more powerful telescopes, like the James Webb Space Telescope and its successors, towards K341b. What they found was astonishing. The subtle dips were indeed consistent with a planet, but not just any planet. This world, which we've now designated Elara 7, was a true circumbinary planet, orbiting both stars, not just one. Its orbit was so precisely aligned and uniquely tilted that it had often been obscured by the glare or gravitational fields of its two suns, making it incredibly difficult to detect using conventional methods. It was a cosmic hide-and-seek champion. Elara 7's orbit is truly remarkable. It's highly eccentric, meaning it's not a perfect circle but more of an elongated ellipse. This takes the planet on a long, sweeping journey that brings it sometimes closer to its binary suns, and sometimes much further away. This unique path, combined with its unusual inclination, meant that for much of its orbital period, it either passed too far from our line of sight to cause a detectable transit, or it was lost in the glare of the system's brighter primary star. It was only when it performed a very specific, partial transit, combined with subtle gravitational perturbations on the stars, that its existence became undeniable. It truly is a planet that dances on the edge of visibility. Once confirmed, the next crucial step was to analyze Elara 7's atmosphere. Using transmission spectroscopy, observing starlight filtering through the planet's atmosphere during transit, scientists began to piece together its composition. The initial results were baffling. While water vapor and carbon dioxide were present, as expected, there were also clear, strong signatures of molecular oxygen, methane, and surprisingly, phosphine. On Earth, these combinations are often, though not exclusively, associated with biological processes. Could these be mere geological phenomena, or were they hinting at something far more profound? The data was complex, demanding cautious interpretation. An eccentric circumbinary orbit means Elara 7 experiences dramatic swings in temperature, from scorching heat when closest to its suns, to frigid cold when furthest away. For life to thrive, it would need incredible adaptability. Perhaps a very thick atmosphere provides thermal inertia, buffering the extremes. Or, more intriguingly, life might have retreated underground, relying on geothermal energy or vast subsurface oceans shielded from surface fluctuations and radiation. Such extremophiles exist on Earth, thriving in conditions we once thought impossible. Elara 7 pushes the boundaries of our definition of a habitable zone to new, challenging limits. The atmospheric data alone was enough to classify Elara 7 as a prime candidate for astrobiological study. But then came the echoes. During extended radio observations, astronomers detected a series of intermittent, highly structured radio signals emanating from the vicinity of Elara 7. These weren't random bursts or natural pulsars. They exhibited a clear, repeating pulse sequence, a non-random pattern that instantly drew parallels to the first hypothetical technosignatures predicted by pioneers of the SETI program. It was faint, distorted, and irregular, but undeniably artificial. It was like hearing a distant, faint drumbeat from across the cosmic ocean. When we talk about technosignatures, we are referring to any observable manifestation of technology used by an extraterrestrial civilization. This could range from radio or laser transmissions, to atmospheric pollutants that aren't naturally occurring, or even large-scale artificial structures in space. The key is that these phenomena cannot be explained by known natural processes. The signals from Elara 7, with their clear periodic and non-random structure, fit this definition perfectly. They were not merely noise, but possessed an inherent order that strongly suggested intelligent design, a deliberate pattern meant to convey information or simply maintain a system. The nature of the signals immediately sparked a heated debate among scientists. Were these echoes from an ancient, long-vanished civilization, or were they signs of an active, ongoing intelligence? The signals were intermittent and seemed to shift slightly in frequency over time, almost as if a power source was fluctuating or a system was degrading. This led some to hypothesize that we were detecting the faint, dying whispers of a civilization that had collapsed or departed. Others argued that the irregular nature could be a deliberate way to conserve energy, or simply reflect a vastly different communication protocol, active even now. The question of their age became paramount. One theory proposed that Elara 7's peculiar orbit, which often takes it far from its binary suns, might have played a crucial role in the survival of any life or civilization. While the eccentric path subjects the planet to extreme temperature variations, it also provides periods of respite from the intense radiation and solar flares frequently unleashed by young or active stars. This cosmic shielding could have allowed a civilization to develop and even build advanced infrastructure, perhaps underground, utilizing the brief periods of closer proximity for energy harvesting, before retreating during more hazardous phases. It's a testament to adaptation and ingenuity in extreme conditions. Building on the radio signals, high-resolution imaging from future space telescopes and deep space probes was aimed at Elara 7's surface. What emerged from the fuzzy images were not just geological formations, but unmistakable geometric patterns on a vast scale. These weren't natural craters or tectonic structures. We saw what appeared to be vast, intersecting lines, large-scale constructions, and areas of unusual reflectivity, particularly near the planet's poles and within subterranean entrances hinted at by thermal imaging. These geometric footprints strongly suggested intelligent design, structures built not by geology, but by purpose. The implications were staggering. The scale of these surface structures, combined with the fluctuating energy output suggested by the radio signals, led some researchers to consider mega-engineering concepts. Could Elara 7 host a Dyson swarm? A Dyson swarm is a hypothetical megastructure consisting of a multitude of independent components, like solar panels or habitats, orbiting a star to capture a significant portion of its energy output. On Elara 7, such a swarm might be smaller, perhaps a network of interconnected energy collectors and transmitters, designed to harness the power of its binary suns and maintain its civilization, even in an intermittent fashion. The echoes might be residual power transmissions from such a system. The discovery of Elara 7 brings into sharp focus the Fermi paradox. If the universe is teeming with life, and some of it intelligent, then where is everybody? Why haven't we detected widespread evidence of alien civilizations? Elara 7 offers a potential answer. Perhaps many civilizations exist in highly unusual, hard-to-detect orbits or use communication methods we haven't yet considered. Or perhaps, like Elara 7's potential inhabitants, they are ancient and their signals are fading, their presence subtle and hidden. The paradox might not be about absence, but about our limited perception and persistence in searching. The potential discovery of an intelligent civilization on Elara 7, even a past one, would be one of the most transformative events in human history. It would fundamentally alter our understanding of our place in the cosmos. No longer would we be speculating about the existence of alien life. We would have tangible, albeit faint, evidence. This shift from if to how and who would ignite a new era of scientific inquiry, philosophical debate, and perhaps even reshape our cultural and spiritual beliefs. The implications are staggering, forcing us to reconsider our uniqueness and our role in the grand narrative of the universe. What are the next steps in unraveling the mystery of Elara 7? The immediate focus is on building dedicated instruments capable of higher resolution imaging and more sensitive radio detection, specifically tuned to the identified frequencies. Long-duration monitoring campaigns are essential to gather more data on the signal's patterns and fluctuations. Eventually, humanity might consider sending a robotic probe, a multi-generational mission, to Elara 7. Such a journey would take centuries, but the information it could send back would be invaluable, painting a clearer picture of this hidden world and its extraordinary echoes. Elara 7 stands as a hypothetical beacon, a testament to the universe's boundless capacity for wonder and surprise. Its hidden nature, its unique orbit, and the tantalizing echoes of its past or present inhabitants remind us that discovery is often about looking in the unexpected places, with new eyes and new tools. The story of Elara 7 is far from over. It's an unfolding cosmic mystery, a dialogue across billions of miles and potentially millions of years. And in listening to these faint echoes, we are not just searching for others, but also learning more about ourselves and our own potential in this grand, incredible universe.